the title of my presentation is AI Reality Check. And as I said, I will try to give you an overview on the main challenges that we have faced and also the key lessons learned during the process of building production-ready machine learning models. I will focus on 3 points. The first one is that the rapid breakthrough is central to the learning process in complex topics, especially in the case where you don't have established patterns. The second topic is about a missing baseline. So a missing baseline means a missing target, and that increases the complexity when building machine learning models. And as I said, I will show once more that 80% of the effort is in the data. We need, as SBB, we need to ensure that our networks are safe, and for that we need to do a railways inspection. Most of the time we did that, and we still do a manual inspection. And this manual inspection is safety critical, but also time consuming. And this was actually the motivation for the project I mentioned, AISI. And in general, rail-based inspection is very challenging. So we have more than 23,000 defects that are detected per year. So we have 51 tracks inspectors, and now we have also 2 diagnostics vehicles. And I think something about 250 observational defect types. So it's quite a challenging environment. So in the process of going from manual inspection to a more automated scalable inspection, in the first step, we deployed actually 2 diagnosis vehicles. And these diagnosis vehicles, which can be seen on the image at the top, have cameras deployed. So we have installed cameras there, and they generate about 10 gigabytes per kilometer. So we generate a lot of image data. And in the second step, we started the AISI project with the goal of analyzing this image data. So in general, so the goal of AISI is based on the image data that are collected from these diagnosis vehicles to detect defects. Defects with the goal of increasing the network reliability, but also to reduce the effort of the track inspection in general. How AISI works is actually quite simple at the high level. We have the diagnosis vehicles which generate image data, so the measurement data. We feed this measurement data to our machine learning models, so infer the data with these models, and after that we produce actually images containing these bounding boxes with detected defects. We have 2 models in production. The first one is about surface defects, and the second one is about cracks. And as I said, the result is actually are these bounding boxes with the detected defects. The roadmap, high level, AISI started as a POC. And the goal was to show that with machine learning, we can have a higher detection rate compared to classical image recognition algorithms. And we could show that we can achieve a higher detection rate, which is higher, about 20–30% compared to classical image analysis algorithms. After that, we developed that prototype and we went in production. So one of the models, which I mentioned, the surface defect models, is in production since 2017, 2018. After that, we started the project AISI, actually, which has now the goal of bringing the models to enterprise readiness level and also to automate the existing workflows. So the training pipelines, the inferencing pipelines, and all the workflows which are necessary to process the data. However, this rapid prototyping, which then went into production, was a key for us, because it initiated actually a very important learning process. And only because of that, we are now able to ask the right question and also to identify the real challenges. And some of the challenges will be covered in what follows. Two of them. First one is the missing baseline. As I said, is a missing target, and that is a very difficult case. If you don't have a baseline, then you don't know on how far you can go or how far you should go. And as I said, the second point is about the data. So let's start with the first one. We have three pillars of inspection. So we have a manual on-site inspection. We have an in-office inspection using a graphical tool. And we have now ASI. So this is the third pillar where we use machine learning to detect the defects. One of the main challenges was actually on how to compare, to which of the pillars should we actually compare our machine learning models. Should we compare them to the on-site inspection or to the in-office inspection? And of course, you have the two possibilities to compare your model to the on-site inspection. However, we came to realize that that is not necessarily a fair comparison, because on-site you have more sensors, like you have the hands, and you can remove the dirt from your surface or from your tracks, and then you can see whether it's a defect or not. It's very challenging to do that based on the images. So we decided actually the baseline is the in-office inspection, and we should compare our models to the in-office inspection, because you have the human analyzing image data in office, and you have the machine learning model which analyzes image data. Of course, the second thing will then be to systematically evaluate the in-office inspection, because we need to know on how good the current in-office inspection is, where are the gaps to the manual on-site inspection. Only by that you know actually your human level performance, and human level performance is actually the upper level of what you can achieve with the machine learning model. So we are not yet there, so that will be actually one of the next steps. As I said, this is our baseline. However, that doesn't mean that the data we gather on site is useless. That data that we gather outside is very critical to actually understand what is the gap between the in-office inspection and manual inspection, because that will give us a hint on which defects we cannot detect based on the image data only. And that will be probably then the next step to decide which sensor we additionally need to close the gap, or to achieve actually the performance, not of this one here, of the in-office inspection, but to achieve the performance of the on-site inspection. I mean, from the user point of view, this is what they actually desire. But we are currently working to close this gap here, and then to close the gap between that one and that one. So it was now critical for us actually to decide that this is our baseline, and that we need to first actually close the gap here. As I said, we are in the process of doing a systematic evaluation of the in-office inspection in order to know on how far we can actually go. The second thing is the data, and there we gathered a lot of experience in the last 2-3 years. I will just give you two examples. Like the first one is we had to fight a lot with the quality of the labels. As you can see here, some of the examples, you can see that the labelers are not very consistent when labeling their data. Some of them will generate bounding boxes which are too wide. Some of them will generate bounding boxes which are too narrow, so you miss part of the defect here. And of course, on top of that, we have things that are not easily detectable in the image. Like this one looks actually like a defect, but it's apparently, if I remember correctly, it's a plastic part on the track. So it's if the human cannot detect that one, then of course the machine learning model will have a challenging time to do that. And the second thing, which is very important for us, is actually the having a consistent understanding of what is a defect and what not is a defect. Here I've entered some examples of defects and their length in millimeter. And if we have a quite a decentralized organizational structure, so we have different labels from different teams that will label the data. And you can see here, for instance, some of them will tell you, say that everything that is everything that is actually bigger than 3 millimeter and upwards is a defect, and some other labelers will tell you that actually also 1 millimeter defect is a relevant defect. And by that you can confuse actually the model, because you show the model the different types of defects, and of course you confuse the model, but you also confuse the human when you produce the results, because some organization will expect that you show everything, even the small defects, and some other will tell you that small defects are actually a false positive. So it's a business issue here to consolidate the expectations, and also to consolidate actually the labeling process. And here we spent actually a lot of effort. One thing that we have established now from two perspectives, from the technical perspective, but also from the organizational perspective, are two processes we call crowd evaluation, the top process, and the bottom process, which is called expert labeling. These are internal names, but their goal is, the upper process is has the goal actually to increase the quality of the training data. So what we do is we select the data out of many candidates, and we send them to a crowd of labelers that will label the same data. They will generate the results, and at the end we have consolidated training data. And by that we hope actually that some of the inconsistencies that I talked about will disappear. And the second process we have established is called expert labeling. The idea is that you select some of the relevant tracks out of your network, and ask the experts to go on site and validate whether what we have detected or what has been labeled is actually defect or not. And this is the high quality data that we get, and by that we hope actually to have a consolidation in terms of the relevance of the defects, the example I showed at the beginning, but also to help these people here agree on the way they label the data. By this consolidation here, we avoid cases in which we actually enforce a consensus, but we don't have a match to the reality. So this is our hope, that by using these two processes, we avoid these two cases. And what you can see as a very simple process on this slide is behind that you have a lot of tools, but also a lot of organizational issues that we need to solve. In summary, fast breakthrough was actually crucial. One can ask whether it's the best idea to go with a prototype into production, but I think it was very important, because only by doing that we are now able to understand our problems. And baseline data are the key. Actually, the model, the machine learning model, is only one of many aspects to be treated in real machine learning systems. And I just show you a part of what we had to develop actually to have production-ready models. Just to give you an outlook on what we plan next, we have 2 models in production, and we plan to develop even more models for the different defect types. So we only cover a small subset of the 250 defect types that we have. And one issue that we need to implement soon is the issue of drift decimation. So we know that the cameras and the images have a drift a bit from one measurement run to another one. And that is a challenging thing, because we cannot track actually the evolution of the defects over time. So we are working on calculating the drift, and out of that building actually a system that will allow us to develop predictive maintenance. And that was all. Thank you very much.